Hello. This unit is going to be on momentum in stochastic gradient descent. And we're going to do some of the same analysis that we did with batch size, but for momentum, and try to relate momentum and temperature. But first, I want to talk about momentum. So this is the standard formulation of momentum that's used in PyTorch. So there's an analogy with a physical system. So in a physical system, you've got, this is some kind of called heavy ball momentum. You've got some, in this case, it's the parameter vector, but you think of it as a ball moving through space, and it has a velocity, and it has a force on it, and it has momentum. So the idea is the velocity, it's going through some viscous material, so the velocity is slowing down. So you multiply the velocity by a number less than 1 to slow it down, and then you add in a force, and the force is the learning rate times the gradient estimate. Okay, so you have a force in the direction of the gradient, but that force acts on the velocity, and the velocity changes slowly, and we update the parameter by the velocity, right? So the velocity it has momentum now, so a given force affects the velocity for a while over time. Okay, that's the equations that define momentum. The theory, why do people do this? There's a theory of momentum that's generally given in terms of second order structure, the rate of change of the gradient in terms of the motion in the parameter space. And you can prove theorems that momentum does good things when you're just looking at gradient descent in convex objective functions. And you want to find that local optimum. But these theorems involve the second order, the curvature of the loss function. And second order analyses in deep learning are somewhat controversial. It's not really well established that second order methods or second order analysis is important in deep learning and very high dimensional applications of SGD. Nonetheless, when you go to PyTorch or you read papers, momentum is often used. So I'm going to try to understand or explain momentum. And the bottom line is going to be that there is also a coupling between your momentum parameter mu and the temperature that that SGD with momentum achieves. So there's a temperature mu interaction. And what I'm going to try to derive is that if you set your learning rate, set this learning rate to be 1 minus mu times the batch size times the standard learning rate, this formula makes the temperature largely depend on just this eta 0. So again, it's a way of training your temperature schedule and then being able to use that temperature schedule with different values of momentum and batch size. So it's an attempt to at least reduce this interaction between temperature and the parameter. And this formula does have empirical support. This is another paper relating batch size to learning rate, but it also in the paper discusses momentum parameters. And it suggests this, or what it suggests is equivalent to this formula. So there's empirical support for this. So I'm going to try to sort of reinterpret momentum in terms of running averages. And that's going to make the analysis easier, simpler. So let's just consider a completely generic sequence of either numbers or vectors. And I want to consider a running average. I go running, and when I run on my watch, it gives me the most recent mile rolling average. So, my speed. I actually don't like that. I'd much prefer what I'm about to say. But if you consider an average of the n most recent values, this is the kind of rolling average. So this is just the formula for that rolling average of the n most recent values. That's a little complicated to compute because you sort of have to remember all of those sequences such that you can, all of those values such that you can take one out and put one in to get the next rolling value. There's a much more efficient way to get what is essentially the same thing. you initialize your rolling average to 0, and then you use this update. So you always add, so you define the next value. So this is t and this is t minus 1. The next value is 1 minus 1 over n times the previous value plus 1 over n times the next value. So this is a convex combination. So it's always maintaining, there's an expectation for this thing. It's always maintaining that the average of this is the same as the average of these values. And you can argue that this is essentially similar to taking the rolling average of the last n. What's happening is the contribution of any one value is decaying exponentially. It keeps getting multiplied by 1 minus 1 over n over time. And that's an exponential decay. And if you look capital N steps back, it has decayed by a factor of e. So every n steps, it decays by a factor of e. So that exponential decay is really focused on the most recent n values. And this is a standard thing. It's used, we're going to see it when we do more elaborate SGD versions. Many of them involve estimating things by rolling averages over the SGD, or these exponential decay averages. In the literature and in PyTorch, in standard formulations, you'll see this formula written, parameterized differently. You'll typically see it parameterized this way, where this beta is 1 minus 1 over n, and 1 minus beta is 1 over n. And so you'll typically see betas that are 0.9, 0.99, or 0.999. And that corresponds to n being, if beta is 0.9, you're averaging over about 10 elements, 0.99, 100, and so on, 1,000. In the slides I'm going to use here, I'm going to write this formulation because I find it more intuitive. It makes sense that this number is a number very close to 1. Okay, so I'm going to try to reformulate momentum as a running average. So this is the velocity equation we saw in momentum. I can rewrite this mu as 1 minus 1 over n. That's just a different way of writing mu. And if I do that, and I want to make this a convex combination of something, I simply multiply and divide by n. And now I can see that Vt is a rolling average of n times eta gt. Okay, so let me say it again. Vt, the standard equation for Vt, is equal to defining Vt to be a rolling average of n times eta gt. Okay, that n times is important in that rolling average. We can alternately, or more intuitively, just take a rolling average of the gradient. Rolling averages rolling averages are very intuitive, right? You're just taking an average over the recent times. So I can just take an average over the recent times of the gradient. Now, a running average, the velocity is a running average of this product, but a running average of this product is just going to be this term times a running average of g. Right? Whether I multiply it inside the sums or after I do the sums doesn't matter. So if I define the rolling average this way, then it's true that Vt is just equal to this multiplier times the rolling average of the gradient. Okay, so we have the rolling. So what we've shown is that the standard formulation of momentum can be rewritten this way in terms of a rolling average of GT and an update where you're multiplying the rolling average of GT by n times eta right? So this is equivalent, completely equivalent to momentum as standardly formulated. But this n is important, right? Because that's effectively changing the learning rate. So what I'm going to do is I'm going to analyze this more carefully and somewhat more rigorously. I'm going to adopt this rule of thumb that what really determines the temperature is the effect of any one training point, any one training example, XY pair, the effect of any one training point on the parameter. How much does this training point change the parameter? So if we were doing batch size 1, that would just be the learning rate times the gradient of that training point. So what I'm going to analyze is for the momentum algorithm, how much does one training point ultimately affect the parameter setting? And the idea is that that is what's determining the temperature. That's what's determining the amount of noise that we're getting in the from the stochastic nature of stochastic gradient descent. So the first observation is that any one training point, the effect that it has on the batch average, since this is a batch average, is 1 over the batch size times that training point. Since we're taking an average, every training point gets divided by the batch size. Okay, and we can make this observation relative to, that's going to be useful in rolling averages. So for a rolling average, the following observation is interesting. If I take the sum of all the weights over time on a given input value. So remember, when we take a rolling average, we add in 1 over n times a new value. And then that value is multiplied by 1 minus 1 over n each time step. So the weight on that value is equal to this infinite sum if we let it go to infinity, but it's decaying exponentially. So it's the fact that it does not actually go to infinity doesn't really matter. And there's this simple observation that this sum of the weights of that when we add a particular example in and then include it in the rolling average, the sum of the effect of that over the whole rolling average is just 1. This sum sums to 1. So we get that the effect of the batch average on the rolling average of the batches is just 1, is just the batch average. So putting these two things together, the effect of a given point on this is 1 over b. The effect of this on the rolling average is just 1. But this is the update we're doing, right? So the total effect of a given training point is n divided by b times eta times the size times the gradient of that training point. Right? The batch size b reduces the effect by b. This update equation increases the effect by n. So that's what I just said. The total effect is this. So if the total effect is this, if I take eta, sorry, it's here, if I take eta to be b over n times eta 0, that means if I take eta to be b over n, then that cancels this b over n, and I'm going to get that the effect of this thing is just eta 0. So, so this rule will make the temperature independent of the batch size and the momentum parameter. N here is the momentum parameter. Or if we take the standard momentum parameter to be 1 minus 1 over n, then we get this, then this expression becomes this expression, which is what I started with in the beginning. And so if we use this expression, the idea is by setting this learning rate as a function of the momentum parameter and the batch size and something that determines the temperature, we get a temperature that's largely independent of the batch size and the learning rate. Okay, thank you.